microscopic point of view. The behavior of a system may be investigated from either a macroscopic, the behavior of a system macroscopic and microscopic. Point of view. Let us briefly describe a system from a microscopic point of view. At first, microscopic point of view. Consider a system contained of a cube of on each side, for example, this cube it contains a monoatomic gas at atmospheric pressure and contain a monoatomic gas at P atmosphere and also T atmosphere, for example, temperature and pressure. The volume contains approximately power 20 atoms. To describe the piston position of each atom, we need to specify 3 coordinates. To describe the velocity of each atom, we specify 3 velocity components. In this case, for the macroscopic point of view, we must describe position of each atom. We need to specify 3 coordinates. For each. So each atom must describe separately with a separate coordinate. We also can be described 3 velocity component for each atom. This is a macroscopic point of view. Thus, to describe completely the behavior of this system from a microscopic point of view, we must deal with at least equation. and unknown. Even with the large digital computers, this is a hopeless computational task. However, there are two approaches to this problem to reduce the number of equations and variables to a few that can be computed relatively easily. One is the statistical approach. For the microscopic point of view, we have a statistical approach in which on the basis of the statistical consideration and probability theory, we deal with average values for the particles under consideration. Statistical consideration and probability theory. We deal with average values for all particles. Under consideration, this is usually done in connection with a model of the atom under consideration. This is the approach used in the discipline of kinetic theory and statistical mechanics. The other approach to reducing the number of variables to a few that can be handled is the microscopic point of view. Of classical thermodynamics. We have also the microscopic of the classical thermodynamics. As the word classical point of view, for the talking about, and next is the microscopic point of view. The other approach to reducing the number of variables to a few, whatever the statistical consideration and probability theory. We have also the other approach that's The other approach to reducing the number of variables to a few that can be handled is the macroscopic point of view. Of classical thermodynamics. As the word macroscopic implies, we are concerned with the gross or average effect of many molecules. Gross or average effects These effects can be perceived by our sense and measured by instrument. However, what we really perceive and measure is the time average influence of the many molecules. Time average influence of For example, consider the pressure gas exerts on the wall of its container. This pressure results from the changing momentum of molecules as they collide with the wall. From a macroscopic point of view, however, we are concerned not with the action of the individual molecule, but with the time average force on a given area, which can be measured by a pressure gauge. In fact, these macroscopic observations are completely independent of our assumptions regarding the nature of matter. Although the theory and development in this book are presented from a macroscopic point of view, a few supplementary remarks regarding the significance of the microscopic perspective are included as an aid to understanding the physical process involved. Another book in this series, Introduction to Thermodynamics, Classical and Statistical, includes thermodynamics for the microscopic and statistical point of view. A few remarks should be made regarding the continuum. From the microscopic point of view, we are always concerned with the volume that are very large compared to molecules. Volume are very large compared to the molecule dimension and molecules dimensions. and therefore with systems that contain many molecules. Because we are not concerned with the behavior on individual molecules, we can treat the substance as being continuous, disregarding to the action of individual molecules. The continuum concept of the course is only a convenient assumption that loses validity when the mean free path of the molecules approach the order of magnitude of the dimension of the vessel, as for example in high vacuum technology. In medicinal engineering work, the assumption of a continuum is valid and convenient. The assumption of continuum is valid and convenient, going hand in hand with the macroscopic point of view.